All right, on Friday, we talked about functions and relations in the notes. And so, of course, you just completed the practice on that. And now we're going to talk about domain and range. So, we're looking at domain and range of continuous and discrete relations. And we're also going to determine whether the relation is a function. So, first of all, let's talk about domain. The domain is the set of input values, also known as the x values or the independent variable values. And that's actually the complete set. So it has to include all of the possibilities for the x values. The range, similarly, is the set of output values. So it's the set of all the y values, which are known as the dependent values. Alrighty, so we have an example here. This first one is a in context problem. And we're given some data that's in a table. This says the table represents different numbers of adults versus student tickets purchased. And they want us to graph the data. So the number of adult tickets is X, and the number of child tickets or student tickets is Y. And so the first one, it says that for 0 adult tickets, there were 8 child tickets purchased. With 1 adult ticket, there were 6 child tickets purchased. 2 adults, 4 child, 3 adults, 2 child, and 4 adults, 0 children. So this is just various transactions, apparently. So let's graph this data. So 0, 8. That would be, notice we have number of adults here on the horizontal axis, which is normally where we put the independent variable. And the number of child tickets is on the vertical axis, which is where we put the dependent variable. So adult tickets is 0 with 8 child tickets. So I'm going to put a dot right here at 0, 8 for that first data point. The second data point, let's see some various colors here. That's 1 adult ticket with 6 child tickets. So that would be this one here. There you go. And then the next data point would be 2 adults, 4 children. So 2, 4 would be here. That was that one. Maybe use red next. So 3, 2, 3, 2 would be here. And then one last data point to plot. I'm going to use green yet. So 4, 0. So that would be here. That was that last one there. Okay, so we need to think about whether or not connecting the dots makes sense. Now, just looking at the data that we have plotted there, it looks like they all fall in a nice straight line. So you may be tempted to connect them, but you actually have to think about the context of the problem to decide whether or not that's a good thing to do. So if we connected them, then that would mean that maybe this point right here would be a point on our line. And that would correspond to 1.5 adults and 5 children. Now, if you think about that, 1.5 adults is not something that that makes sense. You can't have 1.5 adults and you can't have 1.5 tickets. So, so drawing a line through these data points actually does not make any sense, and so we should leave them just as individual points. When you have data that's like that, we call it discrete because only the individual numbers that we have there are included in the data set. So we don't want to include everything in between 1 and 2 and everything between 2 and 3. Alrighty, so when we list the domain is going to be all of the possible x values or independent variable values, which in this case is the number of adult tickets. And the only way that I can do it for discrete data is to just make a set. So I'm going to use set builder notation and say x such that, and then x equals. And then I just have to list the individual numbers that we have So 0, 1, 2, 3, and 4. And I don't have enough information to infer whether or not there were any other data points there. They didn't tell me. For the range is the number of child tickets. And again, I just have to list the data points that we have there, just the Y values. Now, with domain and range, we're always going to list things in order from least to greatest. So even though these points were presented from high to low, I'm going to list them from low to high. So I've got 0 is my smallest, then 2, then 4, then 6, and finally 8. Okay, so now we need to determine whether or not this data represents a function. And just looking at this data here, in order for it to be a function, the x values can't repeat, and the graph would have to pass the vertical line test. So looking at my x values in my actual data set there, oops, I scrolled a little bit too much there. So the x values never repeat here, and if I'm looking at the graph, a vertical line would only pass through one of these points at a time. So any vertical line would only contain one of those points. So it does pass the vertical line test, therefore it is a function. All right, now we're going to look at some continuous data. Continuous data can take any value within the given interval. Discrete data is counted, so it's particular values. Continuous data is measured. So we're going to look at some situations that are described here and determine whether they are discrete, so counted values, or continuous, where anything within the interval is acceptable. So the first one is time spent running versus the number of miles traveled. In order for it to be continuous, both variables have to be have to make sense for all possible values. So time spent running, you can have partial time values. That's perfectly acceptable, like 1.2 seconds. That's pretty normal. Same thing for number of miles. You can go a half of a mile or a quarter of a mile. That makes perfect sense also. So since all of the little values in between the whole numbers on this one make sense, this would be continuous. Which is kind of a hard word to spell. It's got a bunch of vowels there at the end. Alrighty, the second one, the number of candy bars bought versus the total money spent. Now, number of candy bars bought. Now, if you go into a store and you try to buy a candy bar, you can only buy 1 candy bar or 2 candy bars or 3 candy bars. You can't buy a half of a candy bar. The money that you spend could be continuous, but the number of candy bars can't. So this one is actually discrete. Okay, the length and width of a rectangle versus the perimeter of the rectangle. Now the length and width, let's say we're measuring things in feet. Is it possible to have 1.5 feet? I think it is. And since the perimeter is just the sum of the lengths and the width, the perimeter could also be fractional values as well. So this one is continuous. The temperature inside a car over time. Let's see, temperatures. Typically, we don't talk about the temperatures being decimal values, but it actually does include those decimal values. It's just the variance is so slight that for everyday usage, we don't really consider it. But the temperature actually could be 92.3 degrees. Good example of that would be like your body temperature, they tell you is normal, is 98.6 degrees. And then the other variable here is time. And time, of course, is continuous. So this one is continuous. Wow, that got weird. Alrighty then, each customer at the grocery store gets 2 free samples. So let's see, one of the variables is each customer. And let's see, the number of customers, I think that would have to be individual values. Like you could have one customer or you could have 5 customers, but you can't have 3.3 customers. That doesn't make any sense. So this one is discrete. I want to emphasize again, if just one of the variables is discrete, is counted discretely, then the entire data set would have to be discrete. Alrighty, we're going to look at some graphs now. We're going to determine from the graph whether the data that we're looking at is continuous or discrete. The difference on a graph would be is if the dots are connected, then it is continuous. Continuous doesn't mean it goes on forever in both directions. It just means that it includes values in between the points that you actually see, which is indicated with a line or a curve. So actually, let's go through all of these graphs and look at that first. So this first one here, they show me 2 points, and then they connect them with a curve here. So this would actually be continuous. On the second one, it's just a series of dots. We would call this a scatter plot. That's actually real terminology there. But these dots are not connected, so this would be discrete. The third one, I see an open dot, which means not included, of course, and I see 2 additional dots, and then they're connected with a line segment, another line segment, and array over here. So since they are connected, this would be continuous. Got 3 more graphs here at the bottom. Oops. Oh, got a bunch more. Okay, so the next one, I've got an open circle here and a closed circle there. So would this one be discrete? Or sorry, and they're connected here. So would this be discrete or continuous? Well, that would have to be continuous because they're connected. Next one we have here is a mapping. We looked at mappings yesterday. We want to know if this one is discrete or continuous. So the only information we actually have about this one is individual x values going with individual y values. So I don't have the information about the in-betweens, so that means this would have to be discrete. For the next one, looks like I've got a triangle that's graphed. So I'm not seeing any individual points that they put out as really important, but they are all connected. So this would be continuous. I'll leave those last 2 for you to figure out there on the discrete or continuous. Alrighty, so the next thing we're going to do is describe the domain and the range for each of them that are functions. So if it's not a function, this is important. If what you're looking at, you decide that it is not a function, and you're right, then you don't have to find the domain and the range. Domain and range only make sense when you're talking about functions. So for a graph, to determine whether it's a function, we talked about this on Friday, you will use the vertical line test. So with this first one here, could we draw a vertical line anywhere on this graph and have it intersect the curve that's there no more than one time? After thinking about that for just a moment, turns out yes, we can. So because this one is a function, we are going to state the domain and range. Okay, so the domain is all of the possible x values for this graph. We're going to do this in interval notation. So in order to get them in order from least to greatest, which is how it's always supposed to be, I have to look at the graph from left to right. And the furthest left that I see on this graph is this one right here. The domain is the x value, so I need the x value of that point. And the furthest right that this one goes is over here. And again, I'm looking at the x values. So I need the x values between the two extreme sides there. So this one looks like it's at -3, and this one over here is at +3. So my domain in interval notation would be -3, 3. Then I do need to decide whether it's brackets or parentheses on the ends. So remember, a closed dot means included, and a bracket also means included. So -3 is included, so it's a bracket. +3 is also included, so a bracket on that side as well. Now for the range. The range is all the possible y values. And again, I have to get them in order from least to greatest. So on my picture, I want to look at the lowest point and the highest point. Lowest point first, because the smaller y values are lower on the graph. So the lowest that this graph goes is right here. And the y value associated with that is -4. The highest this graph goes is either of these 2 points here. They're at the same level. I'm going to sketch that in there. The y value that's associated with that one is a +4. So this would include all my y values between -4 and +4. So I'm going to write that down. -4 first, +4 next. And then we have to determine whether or not they're included. But the topmost points, we have solid dots. Now, even if just one of these was solid, it would still be included. But a solid dot means included, so this is going to be a bracket on the +4. Now, at -4, at the low point on this graph, there's no dot there, but there is a curve that's connecting it. And what makes up that curve is actually an infinite number of solid dots. So this is actually a solid dot here, even though they didn't put a big black dot on it. So I'm going to use a bracket on that side as well. If they wanted it to be not included at that point, then they would make it real obvious. They'd put a big open circle there. But since that's absent, this one is included. Okay, for the second one, we want to first determine whether or not it's a function. We are looking at a graph, so I would use the vertical line test. So I would want to look at this graph and see if there's any place on here where I could draw a vertical line and it will intersect more than one point. After a moment's examination, I see it won't. So this one is a function. I would say yes. And since it is a function, I'm going to go ahead and find the domain and range. Okay, now this one is discrete data. So that means when I'm finding the domain and range, I'm not going to use an interval because it's not everything between this value and this value. It's just a particular set of x's and a particular set of y's. And for the x's, of course, I do want to get them in order from least to greatest. So I need to read my graph from left to right and then write them down as I come to them. So this first one here is at -3. The next one I come to is at -2. The next one is this one here. Its x value is 1. Oops. The next one I come to is this one. Its x value is 2. And then the very last point that I have on this one over here on the far right has an x value of 5. So I would just list all 5 of those values. I'm going to do the same thing for the y's. We'll use light blue. Okay, but for the y's, of course, it is discrete, so I'm just going to be listing them. Y such that y is equal to, and I want them in order from least to greatest. So remember, I need to start at the bottom of the graph. So I'm looking at the lowest point. This one is my lowest. Its y value is -5. Then I would keep moving up the graph until I get to the next point, which is this one here. Its y value is 0. And keep moving up the graph. I have 2 points on this one. They share the same y value. I don't have to list it twice. I'm just going to list it once. So that's a y value of 1. And then the topmost point here has a y value of 4. So that would be my range. Notice the domain includes 5 values and the range only includes 4. That's perfectly fine. They don't have to be symmetric. All right, looking at the next picture here. Again, it is a graph, so I would use vertical line test to determine whether or not this relation represents a function. After a quick examination, I see that I could draw a vertical line anywhere on that picture, and it would only intersect at most one time, so it is a function. So again, I do need to state the domain and range on this one. This one is continuous, so for domain and range, I can actually give intervals. I can give intervals of values. So I'm going to start for domain looking on the left side of the graph so I can get the smallest possible x value. This is the furthest left that I can see on this picture, and it has an x value of -4. So I'm going to write that down first. And then it's continuous, 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 continuous all the way over here. And then on the end over here, I've got an arrow. That's actually an indication that this continues on forever and ever and ever. Goes on. It's just drawing it forever is not a good use of our time. So we put an arrow on the end of it. Now what that means though, is that when I get to the very end, which you can never actually get to, that means that for the x value, I'd be continuing going out this direction forever and ever and ever. So I would need to describe what happens on that end of the number line. And that would actually be going out to an x value, not really a value, but x approaching infinity. So I'm going to put infinity as the upper bound there. Now for the smallest value, at -4, I have to determine whether to include that value or not. On my picture, there was an open circle, and an open circle indicates that it is not included. So this would be a parenthesis for the -4 to say the -4 is not included, but it includes everything as close to -4 as you can possibly get. And with infinity, you can never actually include infinity, so that one's always a parenthesis. Now for the range, we want the values in order from least to greatest, so we're going to be looking at the lowest that we can see on this picture. And the lowest part of this picture that exists is right here. It's this little flat line. And so there are actually a lot of points in there that include the same y value. But fortunately, we know now that we don't have to write all of those y values. So I just have to write it once. So the lowest is 1. And I do see at least one solid dot on there. And truthfully, since it's connected with a line there, these are all solid dots here. So 1 is actually included. I'm going to go ahead and put a bracket on that one. Then for the upper bound of the range, I would be looking at the highest that this graph goes. And once again, I come across this arrow indicating that it goes up forever and ever and ever. So the y values that are associated with that would be the ones that go up on the y-axis here forever and ever and ever. So once again, that would be toward an infinity, and upward is positive infinity. And also, once again, you can't actually get to infinity. You can't ever include it. So that one's going to be a parenthesis. All right, now take a moment and decide whether these three are functions or not. You should come up with this one is a function. This one over here is not because of this area right there. This one in the middle was a mapping, so we have to go back and shift our brains into the mapping gear there. And for a mapping, it's not a function if you've got more than one arrow coming from an input going to an output. And that actually happens right here. So this one is not a function also. Now for some really good news. Because these last two are not functions, we do not need to state the domain and range. Domain and range doesn't make any sense if you're talking about something that's not a function. So we just need the domain and range on this first one, and I want you to try that. So you're going to pause the video here and then come back and see how you did. Okay, welcome back. So for this first one, the domain should have been from -5 to 5, not including the -5, but including the +5. And the range should have been from -2 to 2, including both the -2 and the +2. Now you may have stumbled a little bit on this one over here and had a hard time deciding whether or not this should be a bracket or a parenthesis. So let's go back and look at that again. Remember I said if it's included at least once, then you include it. So this one includes a solid dot right here, which is a very clear indication, but then it's also got this line here, which is also included. So it's actually included a bunch of times here. But really, it only had to be included once for it to be a bracket. Alrighty, two more down here at the bottom. Once again, I want you to take a moment and just pause and see if you can go through these whole things and then come back and see how you did. All right, so for this first one, they were both discrete data because we only have particular points for them. We don't know for certain whether or not they're connected. The first one, the x value repeats with the first data point and the last data point that they gave us. So this one is not a function, which means domain and range does not need to be identified. Second one, the x values don't ever repeat. They're all unique. So that makes this one a function. And because it is discrete, we are just listing the domain and the range for each of them just by listing out the x values and the y values in order from least to greatest.